Okay, good. So we'll just read the problem and write down the given data first. So in the steam power plant operating in the Rankine cycle, so we have specified the Rankine cycle. So immediately what you have to do, you have to draw the Rankine cycle. So at the starting stages, draw both PV and TS diagram. Later only TS diagram is more than sufficient for you guys. Okay. So since this is a Rankine cycle, since there is an involvement of change in the phase, what you have to do, you have to draw this as well, including the phases. Okay, so how the Rankine cycle would look like is something like this. Okay, I will draw in. Okay, so this is an expansion process. Where is it here? So this is what happens. Some 4 to A, heat addition in economizer, A to B, heat addition in the boiler, and B to 1 is the heat addition in the superheater. So 3 stages of superheating over there. So 1 to 2 is the expansion process where 2 is in the wet state. Okay, and 2 to 3 is a condensation process where the heat is being rejected, and 3 to 4 is a pumping process where the pressure is being again raised. So this is first figure. Second, in case of a TS diagram, how do you write? 3 to 4 pumping process, something like this. So 3 to 4 pumping process. Now 4 to A, you will raise the heat in case of an economizer. A to B, you will change the phase in the boiler. B to 1, again you will raise the temperature using superheater. Now 1 to 2, again you are expanding the things isentropically like this. Okay, isentropically. Next 2 to 3, you are releasing your heat and condensating using a condenser. So this is what it happens. Now, if you observe, there are two pressures always. We will just see ahead. Next, what he has mentioned is, so as soon as he has mentioned the Rankine cycle, we have drawn the PV and TS diagram of the Rankine cycle. Now, next he says, steam enters the turbine at 20 bar. So where is the turbine? Which process indicates the turbine? Expansion process. Which process?
Adiabatic.
The expansion process in the turbine. Which one? 1 to 2, 2 to 3, 3 to 4, or 4 to 1? Expansion in the turbine.
1.
Yes. 1 to 2. So 1 to 2 indicates the expansion in the turbine. So he says the steam enters the turbine at 20 bar. So what can I take it as?
P1.
Very good. So the P1 value is 20 bar. So I would just write, since all this is an isobaric process, I would take this as 20 bar, the boiler pressure, and the other hand also, even all this is an isobaric process. Okay, isn't it? So as indicated by the PV diagram. So I would take all this as how much? 20 bar, which is the boiler pressure. Is that clear? Next. And with an enthalpy of 324A kilojoules per kg. So what is this? Steam enters the turbine at 20 bar and with an enthalpy of 3248 kilojoules per kg. Whether it is H1, H2, H3 or H4, which one it is?
H1.
Very good. So it is the values of H1 which is given. So H1 is equals to 3248 kilojoule per kg. That's excellent. Next, and an entropy of 7.127 kilojoules per kg Kelvin. So entropy in the sense I would take it as S1, which is equals to 7.12 kilojoules per kg Kelvin. Okay. Condenser pressure is 0.1 bar. So what is the condenser pressure? Whether it is P4, P1, P3, P2, what it is? Condenser pressure.
P2.
Yes, it is the value of P2. So since 2 to 3 is an isobaric process, this is 0.2. ಎಷ್ಟು ಹೇಳಿದ್ರಲ್ಲ condenser pressure? 0.1. So this is 0.1 bar. Okay. So since 2 to 3 is an isobaric process, the pressure at 2 is equal to pressure at 3, which I have taken it as 0.1 bar. Okay. Similarly here. So 2 to 3 is how much? It is 0.1 bar. So boiler pressure is 20 bar and condenser pressure is 0.1 bar. Very good. Next. Find the cycle efficiency. So what all he has asked, I will just write to find. Okay, what we have to find is to find the cycle efficiency, that is efficiency of Rankine cycle, as you have done for Brayton cycle, same thing that you have to find. Second, you have to find specific steam consumption. So specific steam consumption. So this is nothing but the mass flow rate of the steam which is flowing. So this would be in something per kilowatt. Why? Because it is being asked as specific steam consumption. This don't worry about this. I will explain you once we complete the efficiency of the Rankine cycle. So first we shall move at efficiency of the Rankine cycle. So how do you calculate, guys? Same old procedure you have to follow. Solution. So efficiency of Rankine cycle or any other cycle, how it is given? Any other cycle, start with the basics, how it is given. Efficiency of Rankine cycle or any other cycle.
Output by input.
Very good. So it is just output.
Output by input.
Input. So here the output is work output, correct? Divided by, it is input is what you are inputting. You are inputting heat. So that
QS.
is applied.
QS.
Correct. So now either of the things you can use. So how many types of works are there in this particular Rankine cycle?
Two types.
Is two types. What are those?
Turbine work and pumping work.
It is turbine work and pumping work. Okay. So turbine work is WT plus pumping work is WP divided by heat supplied. In the sense, heat is heat supplied from 1 to 2 or 2 to 3 or 3 to 4 or 4 to 1. What it is?
Four to one.
So heat supplied from 4 to 1. Okay. Now we will go individually how to calculate these values. Okay. Now, so WT is nothing but whether it is 1 to 2. So how will you calculate in terms of enthalpy? How will you calculate in terms of enthalpy? Yes, anyone? The process is from 1 to 2. It is work done. That
H1 minus H2.
for work it is initial minus final. So it is H1 minus of H2. Now I need the pumping work. So I know the pumping work happens from 3 to 4. For work it is initial minus final. So it is how do I calculate in terms of enthalpy? How do I calculate pumping work? Anyone?
H3 minus H4.
H2 minus H3.
H3 minus H4, initial minus final. Now, I need to calculate QS. I know heat is supplied from the process 4 to 1. For heat, it is final minus initial. So, how do I calculate Q 4 to 1? How do I calculate?
H4 minus H1.
H4
Yes,
minus H1. H1 minus H4.
H4 minus H1 or H1 minus H4? Which one is
H1.
correct?
H1.
H,
H1 minus H1 minus H4.
So it is for work, sorry, for heat, it is final minus initial. So final state is 1. So it is H1 minus of H4. So I will be taking all these expressions as just equation. One. You can calculate. So since workflow is equal to heat flow, you can calculate Qs plus Qr divided by Qs. So even that also you can use. Why? Because your workflow is equal to the heat flow according to the first law of thermodynamics. Even you can use that. So heat rejected is nothing but what I can say. Heat. Where does the heat gets rejected? In which process? Anyone? In which process the heat gets rejected?
2 to
Yes.
3 condensing.
2 to 3.
Very good. So the heat gets rejected from 2 to 3. So how do you calculate for heat when the process is running from 2 to 3? For heat, it is final minus initial. How do you calculate it?
H3 minus H2.
3 minus H2.
H3 minus of H2. So all these equations, I will be taking it as equation number 1 for my convenience. So basically, whatever you want to calculate, I guess you
Excuse me,
need the
sir.
values of. Yes.
So what about that QR, sir? QR, I didn't get that one. QR.
QR is nothing but heat rejected. So out of
Okay,
4
fine.
process, got it? Any further explanation required?
Yeah, gotcha.
Okay, fine. So when I observe all this stuff on all this analysis, I would come to a conclusion that preliminarily for any Rankine process, if I am in a position to calculate the value of H1, H2, H3 and H4, I will be in a position to calculate whatsoever. Am I right? Whatever it is asked, whether it is as work ratio, specific fuel consumption, turbine work output, heat rejection. Yes, I will be in a position to calculate whatsoever which is asked. Do you agree with me? Yes or no?
Yes, sir.
Only one response. What about others? You don't agree with me?
Yes, sir. Yes.
Okay, good. So we'll just try to calculate one by one. So what I will be writing is, I would just write this sentence. We need to find H1, H2, H3, H4. Then we can calculate efficiency of Rankine cycle. Okay. Okay. Let me start this. Okay.
Yes, sir.
Okay. Now, before I start this, I want you to revise this particular thing once again. Now, I will be in a position to calculate enthalpy in different regions. For example, I may have to suppose to calculate on the saturated vapor line. What happened? Any problem?
So you stop sharing screen.
Okay. Now it's fine.
Yes, sir.
Changing my internet connection. I got my power supply back. Just wait. Okay, so please do revise these concepts where I can calculate the stuff on various plots of the PVLTS diagrams. For example, if it is on the saturated liquid line, your H value will be equal to HF at that particular state. If it is in the wet region, you're supposed to calculate by this particular formula which says HF plus X into HFG. On the saturated vapor line, it is directly equal to the value of Hg at that particular pressure. If it is in the superheated region, you have two different ways to calculate the value of enthalpy. The first way is by using the formula Hg plus Cp into T1 minus of T sub. T sub is nothing but the superheating temperature. Or the other way, you can directly pick the value from the superheated steam tables. Is the revision enough? Everyone got this idea?
Yes, sir.
Good. Now come back here. Oh, this is design. So fine. So we shall just try to calculate one by one neatly now. So H1 now. I guess H1 is in which region? Refer the state 1 and say me it is in which region? H1 is in which region?
Superheated region.
Superheated region.
Superheated region.
Okay, I will just copy this. Okay, and paste it here. Okay, for our understanding. Now, just a minute. Okay, so H1 in the sense state 1. So, in which region it is? Superheated region. So, if it is in the superheated region, how many ways I have to calculate my enthalpy? How many ways? How many ways do I have to calculate my
Two ways.
H1? 2 ways. What is the first way? Using a formula or by using a direct table. So either of the ways I can use. Since in this particular problem, the H1 value is directly given, I would take that. Is that clear? I just revised this concepts if the H1 value was not given. Is that clear?
Yes, sir.
I guess the H1 value is given, no? Kottidara ilva? Is given or not?
Given
How much is the value? It is 3248 kilojoules per kg. So I would just write it. It is given value. Next, I need to calculate the value of H2. Okay. Now, if I want to calculate the value of H2, where is my state point 2? In which region?
Wet region.
Wet region.
So, my state 2 is in the wet region. So, if it is in the wet region, how will I calculate the value of H2? Anyone?
HF.
HF plus X into HFG, where all these points are taken at state 2. Is that fine? Clear? Yes or no?
Yes, sir.
Now, can I get the value of HF and HFG from the steam tables?
Yes.
Okay, so now state 2 is at the pressure of how much? State 2 is at the pressure of how much?
0.1 bar.
So 0.1 bar. So now just write from steam tables, at pressure of 0.1 bar, I have the value of HF and HFG as how much? Please give me the value by referring the steam tables.
191.8
191.8. What is the unit?
kilojoules per kg.
Kilojoules per kg. Now HFG
2392.9
292.9 kilojoules per kg. Okay. Is that clear? So I know the value of HF. I know the value of HFG. Do I know the value of X at state 2? What is the dryness fraction at state 2? What is the dryness fraction at state 2? Do I know the value? Do I know or not? Is that particular dryness fraction value is given or not?
No.
Not given.
Not given. See, carefully observe this procedure. Why? Because you'll be using the same procedure for every problem from now. Okay. So, x2, I will just write it here. x2, that is the dryness fraction of 2. Okay. Is unknown. Is unknown. In that sense, what you have to use is this particular process data. Same procedure for every problem, no need to worry. Okay, what type of process is from state 1 to state 2? What type of process it is? From state 1 to state 2, which process? What type of process?
Turbine expansion.
Expansion. Which type of process? Which category?
Adiabatic.
Adiabatic. Adiabatic in the sense, what is the other name for adiabatic?
Isentropic.
Isentropic.
Isentropic in the sense, what it is?
Entropy is constant.
Entropy is constant.
Entropy is constant. That means, can I write it as S1 is equals to S2?
Yeah, sir. Can.
Yes. The same thing I will be writing here. Since X2 and we know that process 1 to 2 is isentropic. Therefore, I would write S1 is equals to S2. Now, I need to find the value of S1 and I need to find the value of S2 and compare these two values. Okay, this is very important, guys. Now, where is my state 1? Where is my state 1?
Superheated region.
So, state 1 is in superheated region. I would just write it here for my convenience. Superheated region. And S2, where is this particular boy? S2, where it is?
Wet region.
Wet region. So, I would just write it here as the wet region. Now, how do I calculate S1 and S2 if it is superheated and the wet regions separately? Okay. Now, S1 is in superheated region. Can I get the value directly from the steam table, or it is given? Whether it is given S1 value?
It's given, sir.
Very good. Then my job is half done already. So S1 value.
Yes, sir. 7.127.
It is 7.127. So that is equal to, so I would just write it in the bracket as it is a given data. Now, how do I calculate the value of S2? S2 can be calculated since it is in the wet region. How will I calculate? Anyone? Anyone? I want to calculate Yes at state 2 and state 2 is in the wet region. How will I calculate? How will I calculate?
So using the formula SF plus X into SFG.
Excellent.
Not.
Excellent. So same thing I'll be using here. It is SF plus X at state 2 into SFG. From where do I get the values of all this stuff? Would be at 2, guys. At state 2. Okay. At state 2. Okay. Now, how do I get the values of SF and SFG at state 2? Anyone, any idea, any hint? How do I get it?
Steam table, sir, from steam table.
So, okay, state 2 is at the pressure of how much?
0.1.
So 0.1 bar. So now just referring, okay, from steam tables at pressure of how much? 0.1 bar. We have what we have, the value of SF and SFG. How much?
$0.6493.
What is the unit?
Kilojoules per kg Kelvin.
Kilojoules per kg Kelvin. Now, SFG.
7.5018.
Kilojoules per kg Kelvin. Now, immediately substitute those in the above equation. So, 7.127 is equal to SF is 0.6493 plus X2, that is the thing we need to calculate. SFG value was 7.5018. So, from this, what is the value of X at state 2, that is dryness fraction at state 2?
Zero point eight.
0 point, yes, Lucky?
8635.
0.86, oh, shit, okay, 0.86, that's it, that's enough, I guess.
35.
Okay, 3.5 or 3.4, whatever it is. Now, since the value of X2 is known, pick that particular value in order to calculate the value of H2. So H2, I will just pick up that. H2, I would pick this equation to substitute all the values which I have calculated. Okay. So H2 is HF, I have taken it from the steam tables. It is 191.88 plus 0.8635 into HFG is 2392.2. If I do so, I would get the value of H2 in kilojoules per kg. So by this, I would calculate the value of H2. Yes, how much is the bandwidth?
Two two five seven point five four
2257.54.
kilojoules per kg.
225 something, 7, huh? 7, huh?
7.
Yeah, 2257, sir.
0.84. So we have successfully calculated H1. H1 directly it was given. H2 we have calculated. Now you try for H3 and H4. Okay. H3 is in unsaturated vapor line, sorry, liquid line. Correct?
Excuse me, sir.
Yes.
Sir.
Hello. Yes.
Sir, can you calculate drainage fraction using that HF formula itself? So HF plus X into HFG.
Dryness fraction using
HF, H1, H2 formula is there, sir. HF plus X into HFG.
HF.
Okay, H2 is unknown.
Okay,
H2 is unknown.
So that is why we have done all.
Yeah.
Hmm?
Yeah, sir. Okay.
So in the next class, we will try to calculate the values of H3 and the values of H4. So again, H3 is in the saturated liquid line, H4 is in liquid state. Again, two different conditions. We will see how to tackle this in the next class. Okay, till then, have a great afternoon. All of you mark your attendance in the Google Sheet and leave the class. If it is already marked, don't worry.
Thank you, sir.
Thank you, sir.
Yeah.
Thank you, sir.